So, in particular, if you are interested, you can come back on Monday to his PhD defense to learn a little bit more about this this stuff. So, the idea it's very simple. Probably you know about these interacting particle systems. There have been various talks about them as maybe some icing systems or easing systems, exclusion processes, zero range processes, even Brownian motions with interactions, all these particle systems. And the main goal, what we like to do with these particle systems is to understand their collective behavior. Okay, so, and this collective behavior comes in the form of usually scaling limits. And usually we call hydrodynamic limits just a fancy name for large numbers. And fluctuations is kind of a fancy word for the central limit theorem or for the large deviations principle. But although these things have a lot of meaning from the point of view of statistical mechanics, that's something that I'm not going to talk about today. But so I just want to tell you that the questions about scaling limits of these interacting particle systems when the size of the systems is large is a very interesting question, a very natural one, and still a very challenging from the mathematical point of view. Okay? So let me just start putting some notation, just to fix the notation to say, so you know what are the objects I'm going to talk about. So n is going to be the scaling parameter. So this number n goes to infinity at some point and represent the scale. So usually the number of particles is a function of n. N goes to infinity, and the mesh of the lattice that we are taking in consideration is going to be 1 over n. It goes to 0. So we are approaching the continuous realm somehow. So I'm going to talk. So there are these particles that move around, and they move on this lattice here, GDN, which is the discrete torus of size n. So you have n to the d sides ordered in this lattice array with periodic boundary conditions. You can do something different if you want to, and maybe your favorite particle systems lives in ZDE or somewhere else. It's not really important. And this omega is going to be the state space of my particle systems. Is the sequence of zeros and ones defined on that state space lattice space. So 0 means that a site is empty, and 1 means that there is a particle at that site. Okay? So in a particular model I'm going to consider today, there are at most 1 particle per site. Okay, just to make things a little bit simpler. And this particle systems is going to be denoted by eta Tn. So T is time, n is the scaling parameter, and eta is a configuration here. So it's a sequence of zeros and ones on this lattice. Okay? So now, to make things more concrete, I'm going to consider one particular example of interactive particle system, which is already have all the difficulties and features, the key features that I want to stress today. So there will be a diffusion dynamics. Okay? So let me just rewrite here the picture so you can see it again later on. So there are particles going around. So let's say particles like this. And these particles, they move following some kind of random walks on which the rates, they are continuous time. Okay, it's easier when you have a bunch of particles to do things in continuous time. The rates at which these particles move are actually depend on what the particles see around them. Okay, so there is some local rule that I'm going to call Rxy that tells you how fast these particles move. So, well, first of all, this jump here is not allowed because there's already a particle there, so there is the exclusion rule. And for example, this jump here is it's okay because there is no particle there. If you call this side x and this side here y, this rate is going to be rxy. And here I'm just taking one particular example of possible rates. So rxy is equal to 1 plus a eta x. So let me write it like this: x plus ei, eta x minus ei plus eta x plus 2ei. Okay, so the idea is that what you put here is not really important. The only thing that I want to stress is that there is interaction among particles. Yes? Okay, yeah. I can use white chalk. So okay, well, so then in that case, please try to memorize this picture for later use. Okay, and so the main thing I want to stress is that these particles have some interaction among them. Because, for example, the case of the exclusion process, which is very popular, corresponds to the choice of this rate r equal to 1. And the exclusion process is a very nice particle system for many reasons. One of the reasons which is nice is it's something I don't like to use today, is that somehow allows you to do a lot of explicit computations. Okay? So it's what sometimes is called a completely integrable Markov chain, in the sense that you can compute basically everything you want, because you can actually almost explicitly diagonalize the transition matrix of the exclusion process. Okay, so okay, that just to let you know, I'm going to call Lx the generator of this diffusion part of the dynamics. Okay, so this is some sort of diffusion because particles move like random walks. The particular form of the generator is not very important. I just put it there just basically for later use as a notation. Something which is important we have to observe is that the Bernoulli product measures are invariant under these dynamics. Okay, that's because the rate at which this guy jumps from here to here, if you freeze all the other particles, is the same as the rate from which the particle comes back. So there is this, so how it's called that thing? It's the tail balance relation that tells you that uniform measures are going to be invariant in the finite volume situation, and then of course Bernoulli product measures are going to be invariant also. Okay, so if you start the system with some IID random variable, so you decide at each site independently whether you put a particle or not with the constant density rho, then this measure is invariant. So that's what I call the diffusion dynamics. So on top of it, there's going to be a reaction dynamics. Okay, so the reaction dynamics is something non-conservative. So one observation that one can do here is that the total number of particles is preserved by the dynamics, because it's just particles just move around, but they don't disappear and they are not created anywhere. So in principle, that's this number is conserved. And I'm going to put an extra part that will not conserve the number of particles that we call the reaction dynamics. Okay, so at a particular site x, you create a particle if there is a vacancy. So in order to create a particle, you need a hole. So you create it with some rate that I'm going to call C+. And you destroy a particle with some rate that I'm going to call C-. Okay, so these functions C+ and C- are also local. That's the only important thing. So they depend on what the particle sees or the hole sees around him. And just to fix ideas, one example that one can consider is the one for which I'm going to state our main results. You can think, for example, that C+ is equal to 1. So whenever there is a hole with rate 1, you create a particle. And C- is going to be equal to 1 plus some constant b divided by 2d, the sum over y minus x of eta y. So what does it mean? It means that now the particles are annihilated with a rate which is a little bit bigger than 1, depending on how many neighbors they have. Okay, so these particles don't like each other, so they try to destroy one to the other, and with that rate. The particular form of the rate is not very important for what follows. Of course, it could be important in applications. This is kind of reminiscent of the so-called constant contact process, but that's for us. Just the fact that they are local is the only important thing. Okay, and I'm going to call LRN the generator of that reaction part, and the observation that this product with Bernoulli measures are never invariant if B is different from 0. Okay? Well, you can check that, see it as an exercise. Then if you combine these two things, you will get a particle system with non-trivial invariant measures. Okay, so actually you cannot characterize the invariant measures. You just can say from the general theory of Markov chain that the invariant measure is unique because this is just a finite state Markov chain, so and it turns to be irreducible. So it does have some invariant measure, but the invariant measure is not accessible for us. Okay. So I'm going to call the Markov chain eta Tn, the reaction diffusion model, if I take this generator here. So what does it mean? It means that, remember that n is the scaling of my system. So I'm thinking about this discrete torus as a discrete approximation of the continuous torus. Okay, so I kind of imagine that these points are at distance 1 over n, one of the others. Then it is natural to accelerate the diffusion part of the dynamics by n squared, because that's the scale at which a random walk do something macroscopically relevant in the limit. And it turns out that it's also natural to do not accelerate the reaction part, because with that scalings, this combination of scalings is exactly the combination at which both effects have the same strength. Okay, so the reaction and the diffusion part of the dynamic have the same strength. If you understand what it means, one way to see it is that with this scaling, both parts of the dynamics, they have spectral gaps of the same order 1 in this case. Okay, so this is the model I want to study, this reaction diffusion model. Now, just a word about scaling limits. So, already in the 70s, so Holley and Struck wrote a series of very influential papers about this kind of fluctuation results for interacting particle systems. So the question they were actually, it seems that they mentioned that this is a question by, I don't remember if it was Harris or Spitzer. So anyway, so imagine that you look at this quantity here. Okay, so this is the occupation time of the origin of my interacting particle systems. Okay, so so without this rho here, I'm going to tell you what rho is in a minute. This is the amount of time that between 0 and t, the origin was occupied by a particle. Okay, so it makes sense to take, probably because it's a Markov chain, there are some ergodicity, this thing here satisfies some sort of ergodic theorem. So it's pretty reasonable to think that if you divide by 1 over t, this guy here converts to some constant that I'm going to call rho. Okay, so then it makes sense to take out rho, and maybe take out the scaling here, and the question is, what are the scaling limits of this thing here? Okay, so Holley and Struck already observed something really intriguing, which is that for many natural interacting particle systems, in order to answer this question, you have to answer one much more complicated question, which is about the scaling limit of the whole density of particles. And then only once you have established this scaling limit for the whole density of particles, you can answer what is the scaling limit of this very simple object here. Okay, so the idea is that this object here, because of the interaction between particles, is really a very correlated object, and it's not is far from being Markovian. So you try to prove some scaling limit in a higher level for a higher for another object which has much more information, which in the limit becomes Markovian, and then you obtain the scaling limit of this thing here as a projection. So that's the idea that they have in mind, Holly and Struck, and this idea was developed and carried on in various situations with some success. And but still, although it's a very simple question, it's a very difficult to answer. And for example, so in the case so this thing here, in the case on which B is equal to 0, okay, let me put it in this point. No reaction. So if you forget about the reaction part of the dynamics, you just take only the diffusion part of the dynamics, then we know that the invariant measure is are products of independent Bernoulli. Then this rho here is going to be that density. Then in that case, you can prove that this thing here converges to a fractional Brownian motion, properly rescaled. No, you have to put some scalings here. So probably in this scale here, you have to take, so you have to divide by something, which is probably n to the 3/4. This converges to a fractional Brownian motion of index 3/4. Okay, so what exactly is a Brownian motion from fractional Brownian motion is not important for us today. The only important thing is that this is a non-Markovian object. Okay, and this is a theorem that we proved with Patricia Gonçalves very recently. And it's kind of surprising that such a simple question was open for so many years. This question was already formulated in the 70s, and only very recently we just showed this convergence here. Okay, so that's one possible motivation for the study of what we call the fluctuations of interacting particle system. Okay, so now let me tell you about the first kind of scaling limit that you can take in this situation, which is a hydrodynamic equation. Okay, so I don't want to state in a very precise way what a hydrodynamic equation is, because as you may have noticed, it's kind of very technical. I mean, there have been various talks during the week about these kind of things. It's technical, but the idea is that the density of particles, when the scale goes to infinity, converges to the solution of a deterministic partial differential equation. Since this partial differential equation is deterministic, we can think about it as a low large numbers. Okay? And the partial differential equation we obtain in the situation of the reaction diffusion model is this one here. So it has this part here, which is the diffusion. It's a diffusion part. So that explains the name diffusion dynamics for that part. It comes exactly from the diffusion dynamics, from the invisible one that is there. And this reaction term here, f of u, comes from the reaction part here. Okay? One can compute actually the diffusion coefficient, is this one. So in particular, it's a nonlinear diffusion equation. And one can compute also the function f, which is given by this formula here. It depends on our particular choices of this rates here. If you choose something different, you will get something different here. For later use, let me introduce this constant here, g of u. This f of u is kind of easy to understand. It's just the average creation rate minus the average annihilation rate. And this g here actually is the sum of those things. It's the average creation rate plus the average annihilation rate. Okay, so this theorem in various forms has been proven by many authors. I can, let me just quote some. In the 80s, De Masi, Ferrari, Leibowitz were the first one to prove this result here for the case on which the diffusion coefficient is linear. So you have A equals 0. So it's in the case of this usual, more integrable exclusion process. All they use this integrability of the systems in a very effective way. And if you want to learn more about that, you can look at the lecture notes by Demasi and Presutti. Then Guo, Papanicolaou, Varadan, and co-authors introduced the so-called entropy methods to prove this kind of results about hydrodynamic limits, this kind of lossless numbers. And based on that, in Kimnis Varadan, they explain a little bit how to handle this kind of situations, this kind of hydrodynamic limits for some sort of a nonlinear diffusion equations. And for the particular case of the reaction diffusion model that we are considering here, the actual proof was carried out by John Alacino, Landin, and Vares. And let me mention that Yao developed a technique which is called the relative entropy method, which is very powerful to prove hydrodynamic limits, and it's going to be somehow, and it's what inspired somehow what they are going to do now. So, as I told you, this is a lossless numbers, okay? If you want to apply these lossless numbers for this kind of scaling limits here, the only thing that you gain here is all lossless numbers too, okay? So, well, here it looks a little bit silly because I told you it was just the Skordic theorem, but maybe you can take situations on which the initial density of particles is not constant. It's something that it's given by the approximation of some macroscopic profile, and this macroscopic profile is going to be carried on by this equation, which means that here, this density, this rho here should be replaced by the density of particles at the origin, which changes with time. So it's a more elaborate, actually, sort of ergodic theorem in that case, and one can obtain, and that was obtained by Claudio Landin, this sort of non-homogeneous lossless numbers using these hydrodynamic limits. Okay, but that doesn't answer the question that I'm asking now. What are the scaling limits of these things here? Okay, if you want to go beyond the lossless numbers, you have to prove the central limit theorem. Okay, so it makes sense to try to look at what is called the density fluctuations of our system, which is basically what happens beyond the lossless numbers. Okay, so then, well, you try to do that, and you try to define something that is going to converge to some Gaussian law, maybe, so something that should have a central limit theorem somehow. And if you think about it just a little bit, let's imagine that at the beginning we start with some product measure, okay, constant product measure. For our system, no Bernoulli product measure is invariant, so this constant product measure is going to evolve in time. It's not going to be, it's no longer, for positive times, it's not going to be product anymore. But let's think about for a moment that we start with product measures. Well, as spatial variables, those are just IID random variables. So they satisfy some sort of central limit theorem. But if you want to include the geometry of the torus into this central limit theorem, you are obliged to talk about distributions, okay? Because in 1D, it's clear what happens. Well, if you take some interval and you look at the number of particles inside that interval, it's just the CLT converts to some Gaussian random variable. But if you want to do something like a functional central limit theorem for these spatial variables, those things will converge to white noises. And white noises has the white noise has this vast taste to be a distribution, not to be a function. So you are obliged to use the machinery of test functions to just to start to think about this kind of fluctuations result. Okay, so that's why we introduce some test function G. And then we define this average here, Okay, so at time 0, I'm taking out basically the mean. Okay, if you think about this initial product measure. Therefore, well, I'm taking here the CLT scaling. I'm summing on G. And it's a very simple exercise about CLT for independent, but not necessarily identically distributed random variables to see that this thing here at time 0 actually converges to a Gaussian random variable, which variance is given by the L2 norm of the function G. Okay? So now it is reasonable to formulate the question about what happens at later times. Okay? So does it converge? If it converges, what are the scaling limits? Are those scaling limits solutions of some sort of differential equation, as in the case of the hydrodynamic equation? And later on, that was, from now on, I'm not going to talk much more about this scaling limit here, but that was what we did with Patricia. We just proved this convergence here, and we proved that knowing that the convergence of this density fluctuation field, you can recover the convergence of this observable here by some sort of projection. Okay, so if you know the limit of this thing, then you can ask about particular observables that can be of interest for you, and take and look at their scaling limits. Okay, so the theorem that we are able to prove is the following. So assume that the dimension D is less or equal than 3. Assume that at the beginning, we are taking an initial condition which is bounded away from 0 and 1. So this is our D-dimensional torus, and what I'm doing, so here is 1. So here is 0. This function here is U0. And what we do is that at each point x here, we put a particle with probability U0 x over n. And we do that independently for each side. Okay, so this is our initial condition. Okay, so that means that eta 0 has lower product over nullis. Then we know that the hydrodynamic limit is given by the solution of the reaction diffusion equation. Okay? And the solution is denoted here by U. So this U here is a function of time and space. So with this initial distribution of particles, and this, well, this is just a technical condition, not very important. It probably can be removed with a lot of effort that, of course, we are not able to do. But this one is more serious, the more than 3. Then we can prove that this density fluctuation field that we defined before converges to the solution of this thing here. Okay? So let's try to understand what is this equation here. Okay? So this W1 and W2 are two standard independent white noises. So they are space-time white noises. Okay, so this is going to be an stochastic partial differential equation. And the structure of this stochastic partial differential equation is the following. So you have this term here, which is the linearization of the diffusion part of the hydrodynamic equation. There is a prime there that I'm not sure if everybody can see. So this thing here is also the linearization of the diffusion, of the reaction part of the hydrodynamic equation. So we have on one side the linearization of the hydrodynamic equation, okay, which makes sense because we are looking at small perturbations, small fluctuations around the hydrodynamic limit. So it's natural that these small fluctuations somehow evolve following a linearized equation. But we also have some random components, okay, 2 of them. It's reasonable to have 2 of them because we have 2 parts of the dynamics. We have a diffusive part and a reaction part. The diffusive part comes from the diffusion of particles, has to conserve the density. That's why this stochastic term is inside the divergence here. Okay, so divergence of white noise is a type of noise that preserves density. Okay, and there are some complicated coefficients in front of the white noise that you can make sense of them through test functions. And the second noise, which is not conservative, is outside the derivatives. And this one is multiplied by this thing here, which is the data function that I told you before. Is the superposition of two effects, the creation of particles and the annihilation of particles. Okay? So this is the theorem that we can prove, and we are kind of proud of it, because it was kind of a long-standing open problem in the literature of hydrodynamic limits. Of course, this sort of density fluctuations have been treated before. There are many articles about them and a lot of results. But somehow what was lacking in the literature was some sort of robust method that could be applied in some degree of generality. Okay? Most of the results in the literature, they are fall into two categories. Either they consider systems starting from the stationary state, and to start your system from the stationary state, you first need to characterize this stationary state in a satisfactory way, which is not possible for the reaction diffusion models we have here. Or they are in some way totally integrable. So there are some combinatorial structure behind that allows you to perform exact computations. Or there are perturbations of those totally integrable systems. Okay, so in the case on which you know what the invariant measure is, and you know that it has good properties like a spatial mixing or products of IIDs, things like that, Herbert Rost introduced something which is called in the literature the Boltzmann-Gibbs principle, which is a tool that allows you to prove this kind of results. So, and with Brox and Ross, they prove it for the zero-range process, and the Masi, Presutti, Spon-Wick prove this result for the case of a diffusion system without the reaction part. And then, using the entropy methods of Guo, Papanikolaou, and Vardan, Chang showed this fluctuation result for a system like a weakly asymmetric exclusion process, for example. And all of these results, they require reversibility. Not only that the invariant measure is explicit and well-known, but also that the dynamics is reversible with respect to that. So the data results also do not apply for the reaction models that we consider here, because these reaction models are not reversible. And the reversibility assumption under this stationarity was removed by Chang Landinola. So, and that's the story from that point of view. And then there are lots of papers dealing with systems in equilibrium or in stationary states and looking at the fluctuations. So those methods, the method introduced by Chang is very robust and allows you to do that. And then, when A is equal to 0, remember that A, well, you don't see it, but I will point it anyway, was the interaction among particles. So these particles in the diffusion part, they interact more, just not only because of the exclusion rule, but they have a real, like two-body or three-body interaction, and that's measured by this parameter A. When A is equal to 0, we are in the situation of the exclusion process on which there is I told you it was totally integrable, and in particular, something called the BBHGY hierarchy can be used to obtain this fluctuations result. Okay, and this was implemented by the Masi, Ferrari, Leibovitz, as I told you before. In the lecture notes by the Masi and Presutti, they collect a huge number of possible situations on which you can effectively use this type of arguments to prove these scaling limits. And just to quote something recent, and of course, because Patricia is one of my favorite co-authors, Gonzalez and Landin, they prove using this kind of arguments the fluctuations for the weakly asymmetric exclusion process in contact with reservoirs. So, as I told you, when you're not in the stationary situation, or when you're not in the total integrable situation, you are stuck, okay? There is only one, as far as I know, article dealing with that situation, which proposes some sort of robust proof of this kind of results, which is this article by Chang and Yao. So they prove that in dimension 1, the Ginzburg-Landau model has a well-defined scaling limit at the level of fluctuations given by some stochastic differential equation in the format they presented before. But Chang Yao has some limitations. The first limitation is that it's basically impossible to read. I was not able to read it only after we finished our own work that I started to understand the things. And moreover, they require various things that we don't require. So you need to know that the system you're considering has an invariant product measure. And that, with respect to that invariant product measure, you have the log Sobolev inequality. Okay? If you are trying at some point to prove the log Sobolev inequality, you know that this is that's a problem, because the log Sobolev inequality is really something very difficult to get especially in the situation in which you have conservation laws. Okay. So, as I told you before, we don't know the invariant measure for our reaction diffusion system. Even if you knew it, it's not clear that you have the log Sobolev inequality. And moreover, if you want to go to higher dimensions, you really need to do something new. Okay? And this something new is the following theorem. So this theorem, I like it a lot because it's a very simple theorem that can be understood without all these fancy words about distribution and SPDEs and white noises. So it's an entropy inequality. Okay? So if you know that your particle system has a hydrodynamic limit, you know that the density of particles approaches some macroscopic density, okay? This density UT. Then it is very reasonable to think that at least as a first or even zeroth order approximation, the law of your particle system is can be approximated by this thing here. Okay? So what does it mean? Okay, this measure mu Tn is the following. At time t, you look at what is the density at each site x that you should have in terms of the hydrodynamic equation, and you put particles independently at random with that density. So it's a density that depends on space and also changes in time. So this mu t is not the law of any Markov chain, which has to be, maybe it's close to this one. So it's not going to be something that evolves in time. It's just at each time you do this law and you use it as a test. So as an approximation of the real distribution of your interacting particle system. Okay? So you call Ft the density of your interacting particle system with respect to that measure. If this measure is a good approximation for the real distribution of particles, then this Ft should be close to 1 in some sense. So you say, well, then let's try to define some sort of metric that tells you how close to 1 is this density here. Since, well, we know about the work of Yao, okay, so Yao says that maybe relative entropy is a good distance, okay? Of course, you also like it because it has a physical meaning, okay? So it's always a good idea to try entropy. And actually, if you define this HNT as the relative entropy of the real law of your particle system with respect to this approximated law, we have a theorem. So the theorem is the following. So this entropy is bounded by some constant. This constant here, although it's exponential in time, this exponential in time doesn't really bother you because this time is the macroscopic time. Remember that the process, at least the diffusion part, is accelerated by n squared. So if you're looking at the hydrodynamic equation, you're looking at your system at a fixed window of some time length t. So that means that this exponential here is just a big constant for our practical purposes. And then we have here some the bounds depending on the dimension. So it's so entropy is bounded independently of n in dimension 1. Entropy is of order log n in dimension 2, and of order n to the d minus 2 in dimension d equals to 3 or bigger. Okay? So let's take a moment to see why this is a very strong inequality. So if you think a little bit about it, you see that generically entropy should be of order n to the d. Because basically, at each site, if you have a different law, you have you are at distance 1 in entropy, and entropy is additive. Okay. So if you don't believe in this so hand-waving explanation, you can think about something more concrete. If you take two different product measures, independent, so you can compute everything with different densities, and you compute the relative entropy between these two product measures, you get something of order n to the d. Okay? And for example, in dimension 1, the fact that entropy is bounded is a very strong statement, because it's telling you that no matter what observable of your system you take, no matter what random variable that which as a function of your particle system you define, this thing is going to be tight. And any limit point, it has to have limit points. And any limit point has to be absolutely continuous with respect to the limit point of just IID random variables. Okay, so it's a very strong statement. Well, it gets worse with dimension, but you still have a lot of room to move. So just to compare with the existing results, so as I told you before, this relative entropy method of Yao was kind of the starting point for us, and he proved a bound for the same object, this entropy, which is of this form here. Basically, he proved that entropy is of little o of n to the d, and we are proving that entropy is actually of big O of n to the d minus 2. So we are winning almost a factor n squared with respect to the best previous available result. Okay? So actually, this bound here of Yao is enough to get the large numbers. But it's really far from being enough to get the central limit theorem. Okay? So I want to stress that this bound on the entropy is holds for any dimension. And this idea can be useful in many contexts, because it's just a comparison result about Markov chains. And it turns out that for the original problem that we were looking at, this one here, this entropy control was enough to prove it, but only up to dimension d equals 3. The reason why you have this obstruction. Actually, it's a real obstruction. Because if you look at this equation here, let's say that you start our system, reaction diffusion system, from a Bernoulli product measure of some density rho. Let us take this density rho as a stable point for the hydrodynamic equation. So the hydrodynamic equation, reaction diffusion equations, they have various stationary solutions which are exactly at the zeros of the function f. So you can check that this function f has a zero somewhere, and that is a stable stationary solution. So in principle, if you take that as an initial condition for the particle system, you get something that doesn't move too much from that. Okay, so and what you can prove is that here all these coefficients are constant. So you have that the limit converges to this thing here. If you look at this equation here, you can check that the white noise, which should be the limit of the independent thing, is not invariant. Moreover, this thing here does have an invariant Gaussian measure, which is actually related to the Gaussian free field. And if you try to, of course, the Gaussian free field and the white noise are not absolutely continuous. So you cannot talk about entropy, relative entropy between them. But something you can do is that you can take some modifier and make some smooth version of them, and then you can compare the entropy, and you can check that the relative entropy between these two modified versions of the Gaussian free field and the white noise, they diverge with exactly this exponent here. Okay? So in that sense, the result we have here is the best possible. Okay? So if you want to extend this theorem here for dimensions bigger than 3, you really need to start to understand how to use this Gaussian free field to construct a better, where is the approximation? Here. A better approximation for the law of your particle system. Okay? How much time do I have? I think I'm almost done. 2 minutes. Okay, if I have 2 minutes, just let me tell you a little bit about how you prove this thing here. So, well, if you want to prove that something is bounded, something that you can do is that to prove that the derivative is bounded, just like Hugo and Vincent were telling us somehow, no? And so you take the derivative, and you bound it by 2 terms. Okay, so if you take an invariant measure and you take the entropy, this is going to be decreasing in time. So this is the factor, the usual factor you have there. But you have a correction term. Okay? If in this correction term here, if you choose your reference measure in the proper way, you get something which has a chance to be small. In our case, what we do is that we choose the reference measure in such a way that all linear and constant terms here cancel, and you can express this in here as terms which are products of at least 2 occupation variables. Okay, so they are like polynomials of order of degree at least 2. It turns out that when you have polynomials of order at least 2, there is something called the second order Boltzmann-Gibbs principle that we introduced with Patricia, and in the form and which was proved for the kind of functions that appear here in a paper with Patricia Gonzalez and Mariel Simon. That gives you a quantitative estimate on the expectation of this object here. That involves this factor here. Okay? So, well, if you believe in all of that, then you are likely to be able to obtain something that reminds you of the Grongal inequality, and then you get some bound on the entropy H. Of course, the main problem is that this second order Boltzmann-Gibbs principle, with Patricia, we prove it in equilibrium. So here we have to prove it out of equilibrium. It turns out that that can be done with some sort of renormalization procedure, and that will that will give you here something that turns out to be a some Gromwall inequality for H. Okay? Well, thank you very much. No, not dependent on anything of that. Not at all. Doesn't matter at all.
That's because you subtract the density, right?
No. It holds for any. You can put whatever you want. It doesn't depend on the fact that you are a subcritical or supercritical. You can put whatever local creation and annihilation rate C you want. That the result is still holds. Yeah, of course. In hydrodynamic limits, actually, we always do it in finite volume because infinite volume is really